All right, today we're looking at 2.1, Transformers, Shifty Ys. And our key objective today is we're going to perform transformations of quadratics. So in other words, we're shifting or transforming graphs. So here's our situation. Optima Prime is designing a robot quilt for her new grandson. She plans to have a square face. The amount of fabric that she needs for the face will depend on the area of the face. So Optima decides to model the area of the robot's face mathematically. She knows that the area A of a square with lengths, side lengths x units, which can be inches or centimeters, is modeled by this function. A of x, meaning the area, equals x squared, square units. Match each statement with the area to the function that models it. So we got three things. We want each side length is increased by 5. Each side length is multiplied by 5 units. The area of the square is increased by 5 square units. So this is area. The area of the square is multiplied by 5, whereas these two are lengths. Okay, over here on the right, notice you've got A, B, C, and D. I want you to go ahead and pause the video for a second. I want you to think about where each of these equations would match up. Okay, so let's take a look. If we're doing the side length, think about your square, right? If your square had lengths x and x, that's where I got x squared. And we're increasing each of those sides. Now each of these sides is x plus 5. And then we're squaring it, so the correct equation here would be B. Okay, if each side length is multiplied by 5, so this time around those sides each being x, they're going to be multiplied by 5, so it's 5x, or x times 5, right? Times 5x. So, hey, we get 5x squared. The correct answer there was C. This time, the area is increasing by 5 square units. So it's saying, hey, I've already got this area, which we said was just x squared. And if we increase that by 5, we're adding 5. So that's D. And then if we take that area and multiply it times 5, we would have got A. So we're going to take a look, and we're going to see kind of where these equations come from. So on number 2, we're going to look, and it says Optima started thinking about how the graph would change. She decided to look at a few different examples. So we've got y equals x squared plus 2 and y equals x squared plus 3. Look at both the table and the graph for each, and then what impact does it have on the graph? And then what would you draw about adding or subtracting a number from x squared? So let's first, for a minute, let's just think about x squared. So let's think about our x's and y's. So let's let this be just general x squared, because we haven't actually graphed a quadratic yet. So if I plugged in -3 times a -3 is a positive, and then 3 times 3 is 9. What about -2? -2 times -2 is going to be a positive. 2 times 2 is 4. Do the same with 1. -1 times -1 is 1, a positive 1. 0 squared is just 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. So the graph that you get here, this is going to just be kind of a sketch. But we'll go through 0, 0. 1, 1 is a point. But then once you get to 2, you're all the way up to 4. And you'll notice that the other side looks pretty similar, right? So it does make, we've seen this graph once before, it makes this U shape. Okay, so now let's think about what these other things do. So if I do this next one, x isn't changing at all, but now I'm having y equal x squared plus 2. Well, whether you plug in some points, so let's just do a part of the table this time. Let's do -1 to 2. Sorry, -2 to 1. If I do -2 squared, I still get 4 again, and I'm adding 2, so I get 6. If I do -1 squared, I get +1. I'm adding 2, I get 3. 0 squared is 0, adding 2, I get 2. And then I get 1 squared is 1 plus 2 is 3. 2 squared is 4 plus 2 is 6. Another way you could have done it is you could have looked at the y values over here in our table in purple, right? And you could have just added 2 to each of those. So 2 plus 4, when you look at -2, right? Oops, sorry about that. When you look at negative 2, you get 4, so adding 4 plus 2 gives you 6 as well. That would be another way to think about it. As you think about whether you think about plotting those points, or in a moment, maybe I'll pull up the graph as well. But this time it starts a little higher, but then the graph looks about the same. So it looks something like this. So notice the shape of the graph hasn't changed. My scale is maybe like a little bit off, so it looks a little bit wider, but still the same shape. The only thing it has done is moved up. So last but not least, if I take x, and then I have y equals x squared minus 3. So this time, let's think about those same values. Negative 2 to 2. And for the record, you could choose other values, but these will work. We're going to do the same thing. Square negative 2, we get 4. We're subtracting 3, we get 1. Square negative 1, we get 1. We're subtracting 3, we get negative 2. Square 0, we get 0. Subtract 3, we get negative 3. And then as you continue on, you do get negative 1 and 1 again. So this time, our graph, while similar, it's going to start down at negative 3, move up 1, and then here as well. Oops, sorry, didn't quite do that right. 2, 1. There we go. Oops, got to connect my points. So we get the same graph, but slightly kind of different notion there. Slightly different position. Okay, so if we wanted to talk now about like the key ideas then. Here, notice if you add a number, so like in this green one, if we add a number, it shifts up. And if we subtract a number, it shifts down. Okay. So now we want to take a look, and Optima's like, hey, she felt pretty good. That was not too bad. It was pretty easy. So she decides to investigate the effect of a multiplier A. So putting some number out front. Be positive, negative, fractions, or integers. I'm going to go ahead and I'm going to pull up decimals for a second. I think this will help you kind of see what happens, right? Give it a moment to start up. So we were looking to set this x squared to begin with, right? And we even just did x squared plus 3. Right, and x squared minus, I think actually, sorry, it was plus 2, minus 3 and plus 2. Okay, so now that we've got that there, you can kind of see, hey, look, the graph, all that happened was it went up and it went down. Okay, right? So we've got that. So now I'm going to leave that there just as a reference, and now I'm going to do a different one. I'm going to call A x squared. And we've got this slider A. So right now, the purple graph is exactly on top of A. But let's see what happens as I make A more positive, and bigger numbers. How would you describe that? So starting where we began, and if I make A larger and larger, what's happening to A? It's getting narrower and narrower, right? Okay. Now let's look. Let's see if I can do numbers that are less than 1. So notice now, it's like 1. We got 0.8, we got 0.7, 0.6, 0.5. What happens here? It's getting wider and wider. Okay, let's look at what happens when it's negative though. All of a sudden as I reach any of these negative numbers, do you see how the negative flips it over that x-axis? If I go back to positive, it's above. Negative, it's below. Above, below. So the negative is the one that flips it over the x and y-axis. And then if it's bigger than 1, it makes it narrower. And even notice like here, the absolute value is bigger than 1. That's still narrower. But if you get these decimals that are smaller than 1, whether they are negative or positive, that's when it's a wider graph. Okay, so let's write down some of those thoughts. So here we're going to say, okay, so if A was negative, that's when it flipped over the x-axis. And then if A is like bigger than 1, I'll just say that, but generally we mean like, hey, that could be it's also less than -1. Then it gets wider. And if A is between 0 and 1. Oops, I just wrote that wrong. That's the wider one. And this one is skinnier. All right, so let's talk about the type of transformation. So we've done the plus k, and we say that shifts up k units. If we subtract k, we have shift down k units. Both of these are called vertical shifts, meaning they happen in the vertical direction. Okay, I'm going to skip that one for a minute because we'll look at the graph. A negative is a reflection over the x-axis. And then this one is the one that has 2. If A is greater than 1, and you can think that's also going to be, hey, if it's negative, think it's, hey, a reflection and doing this. That's when it gets, I'm going to call it like skinnier. But we technically call that a vertical stretch. And then if 0 is less than A is less than 1, that's a fancy way to say A is between 0 and 1. That's when it gets wider. And our fancy way to say that is a vertical compression. So meaning we're squashing it vertically and it looks a little wider. So let's look at this last one when we add or subtract that H. So let's try it again. We've got X minus, or maybe I should do plus. Let's do plus H squared. Okay, so we got a little slider here. Notice, okay, oh, I should change the color. Can I change the color? Okay, this is the graph we're on. As I make it more and more positive, look at, so hey, this is where we started, right? We start with 0. That's going to be x squared. As I make it more and more positive, which direction is it moving? It's moving to the left. Okay, if I start at 0, I make it negative. Think about adding a negative is the same as subtracting. It moves it to the right. So here, the only tricky thing is inside the parentheses does shift it right and left, which makes sense because that's kind of grouped with the x's, is it's the opposite. So this shifts, shift left 8 units, and then shift right 8 units. And these we both call horizontal shifts. Okay, so now let's go ahead and get some practice. So as we look at these graphs, which the fancy word for a quadratic graph is a parabola, all quadratics equations have a vertex, which it can either be a max or minimum point, and it is the turning point of the graph. The quadratics are symmetrical across this axis of symmetry, which runs the vertex. So you see there that dashed red line, and then the vertex is there at the bottom. So here, our vertex is this point right here. And if I write it as an ordered pair, it is the ordered pair -4, 2. This is a minimum, meaning it is a low point, not a high point. The axis of symmetry, which I abbreviate with AOS, it is, in this case, since it is a vertical line, it is going to be an x equals line. And in this case, it is x equals 1. I totally wrote that vertex wrong. No one corrected me because you're not here. But that's -4, 1. Okay, let's do it again. Over here, the graph to the right, we want to identify the vertex. So the vertex is right here. It's that point. So the vertex here is the point -1, 2, 3, -3. And then 4. Since it is a high point, it is a max. Now let's look at the axis of symmetry, right? If you think about that line where you could fold the parabola over and have it land on itself, the axis of symmetry is once again that vertical line. In these cases, they'll always be vertical, so it's x equals, and in this case, it is that -3. So something to note here, notice this x value here, right? This x value matches the x values from your axis of symmetry. Once again, I'm looking back and I just said the same thing here. My vertex still written incorrectly. I wish you guys were here. This is actually the point 1. Oh my goodness. What is going on? There we go. 1, -4. Okay, now things match up. We had the axis of symmetry written correctly though. This 1 is that x value that matches. Okay, so now let's practice writing some tables. So fill in the following tables or write the equations. Identify the vertex axis of symmetry does have a max or min. Okay, so in this case, right here when it has the +2 on the outside, you should know that's going up 2. So in general, I'm going to leave my x values kind of the same that we were doing in the front, that -2, -1, 0, 1, 2. This time all I'm doing is if I wanted to think about my original y values, maybe I'll write them over here on the side. They were 4, 2, 0, 4, 1, 0, 1, 4. And we did that on the front. This is just x squared. So if all I'm doing is going up 2, I'm just adding 2 to each of those y values. So this is 6, this is 3, this is 2, this is 3, this is 6. The other way to think about it is -2 squared is 4. You add 2 more, you get 6. Okay, so if we now ask ourselves these follow-up questions, the vertex, a little hard to tell here, but can you guys kind of see where it's symmetric about? As you look, you both got a 6, you both got a 3, so the vertex is this point here in the middle, right? So the vertex is at 0, 2. Is that a high or a low y value? That is a low value, so that is a minimum. And our axis of symmetry is always that x equals of the vertex, so x equals 0. Okay, let's do it again. So this time it's inside, and the inside, you can say insiders lie is a quote I've heard before. So it's the opposite. So this is moving it right 1. So I'm going to leave my x values the same this time, actually. Sorry, my y values the same. Those don't change. But for those y values, I'm now going to change my x values. So my x values need to add 1 to each, right? It's going right 1. So rather than being at -2, it's going to be -1. Rather than being 1, it's being 0. Rather than being at 0, it's 1. When x is 2, right, and then 3. Another way to think about it is you could have taken x values, right? So if I took 2, 2 minus 1 is 1, 1 squared is 1, right? So you could have taken different x values and seen that as well. Okay, so then this one, we're looking for the low y value, which looks right here, or a high one, it's symmetric on either side of that. So your vertex is at 1, 0. Once again, this is a minimum, right? It's a low point. And the axis of symmetry is x equals 1 from that x value of the vertex. Okay, this last one I threw a little bit of a curveball at you. We're going to have to write the equation. So notice my x's have not changed. So I'm doing something with the y. So I've got x squared. And then if I went from 4, if we look over on the far left, to 5, I went from 1 to 2, I went from 0 to 1, 1 to 2, 4 to 5, I just added 1 to each of those y values. So our equation is x squared plus 1. As we look for a low point, in this case it is 0, 1. So that is a minimum still. And our axis of symmetry is x equals 0. Okay, 2 more things we're going to look at. We're going to look at the area models for like multiplication, or you can just think about like for quadratics. So to create an area model of a polynomial, we'll choose a small unit square to represent a number, a rectangle to represent x, and a large square with a side length x to represent x squared. So notice here on the right, our little unit squares, you see these little like ones, and then x has just this length, right? This is length x, such that that's a 1 by x, so that's just x. And then when you have two x's, right, this is x and an x, we get x squared. So this one, we could write it a few different ways. If I look at the area model here on below, I've got an x squared, right? If I count up all my x's, I've got 1, 2, 3, 4, 5, 6. So I've got plus 6x. And if I count out all the ones, 1, 2, 3, 4, 5, 6, 7, 8, 9. So plus 9 ones. Okay, another way to look at this, and this is equivalent to, if you look on the outside, you've got an x, and then you've got 3. So you get x plus 3 on the outside. If we look at the other side, I've got an x, and I also have 3 more. 3 unit squared, so x plus 3. So you could use that like we did with parentheses and do x plus 3 times x plus 3, which another way to write that is a fancy way, x plus 3 squared. So let's look at this next one. We got 2 more examples here. This is our x squared. This is our x, our 1 unit. So I could write that as x squared. I've got 2 x's, so 2x plus 1. If we want to be fancy, though, look at the outside. This is length x. This is length 1. Length x, length 1. So what do we have on the outside? We've got x plus 1. And we have another x plus 1, so we could write that as x plus 1 squared. This one's a little bit different, right? These are all x squareds, right? So using the same thought process, I could add them all together, and I've got 4 x squareds. Or if I look at the outsides, these have length of x. Right, so this length on the left is an x plus an x, which is 2x. The length on the top, x plus x, which is also 2x, or you can be fancy, 2x squared. Those are equivalent statements. Last but not least, we're going to simplify square roots. So we're looking for perfect squares or quantity being squared, and we're going to rewrite them. So simplifying the following square roots. I would literally think about this as, hey, what's the square root of 64 times what's the square root of x squared? So if it helps you to break it apart, you can do it, or otherwise you could just ask yourself in your head. Square root of 64 is 8. X squared and the square root cancel, so we just get 8x. Okay. This next one, we've got a squared and a square root. So those do cancel each other out. And if that cancels each other out, we're just left with what's inside, x plus 1. What do you notice about the next thing? You've got a squared and a square root. Hey, so once again, those cancel each other. So we're left with what's on the inside, 4x minus 3. This one you're probably going to want to break down, right? Square root of 36, square root of x to the 4th, and square root of y to the 10th. Square root of 36 is 6. X to the 4th. That one you may want to kind of say to yourself, well, I have 4 x's I'm multiplying by each other, and I'm pulling out pairs. So how many pairs do I have? I have 2 pairs, so this is actually x squared. Right? Or you could say, what times itself? X squared times x squared gives me x to the 4th. Same thing with y. Y to the 10th. I have 10 y's I'm multiplying each by each other. So how many pairs can I pull out? Well, I can pull out 5 of them. So y to the 5th. Or y to the 5th times y to the 5th equals y to the 10th. Okay, good job. Go ahead and try the 2.1.